Good morning and welcome to section 11.4, Infinite Geometric Series. So today we're going to talk about what happens when I have an infinite geometric series instead of a finite one, and it's going to be kind of interesting. Before we do that though, let's see if you remember what we learned last time. So please pause the video and see if you can find the sum of the series given here. And I'll give you a hint. Remember, our sum of a series formula for a geometric series was this. So in order to use that formula, I need to figure out what A1 is, what R is, and what N is. So go ahead and pause and give it a try. Alright, so quick reminder, our geometric formula says that I've got A1 times R to the n minus 1 power. Following that, A1 is 3, R is negative 2, and then to find my n value, I look at my summation notation and I see that this one goes from 1 to 12, so my n is 12. I plugged it all in and you should have gotten negative 4,095. Alright, so now we're going to get into the infinite part, and I need to show you something. So don't write this down right now, just watch. I want to show you why this could possibly be different than what we learned yesterday. So let's suppose that I had this series, and again, you do not need to write this down. I'm going to go kind of fast because I'm just going to explain the why of how this happens. But let's suppose I had this series. As you can see, the bottom number every time is being multiplied by 2. Here's what happens. If I just add together the first term in the series, that's just 1/2. If I add together the first two terms, that ends up being 0.75. If I end up adding together the first three terms, it ends up being 0.88. If I end up adding together the first four terms, I get 0.94. And I want to just tell you, as I add more and more terms, this sum is not going to change very much after a certain point. And now the reason is, if you look at what's going on here, as soon as I get to something like 1/64, that is 0.015625. But let's say that I'm all the way to much later in my sequence and I'm trying to add together 1/256, for example. Eventually, these numbers I'm adding are going to be smaller and smaller and smaller and smaller, and eventually all these numbers I'm adding are so small it's kind of like adding 0 and adding 0 and adding 0. Because if I have, let's say one of my terms in my sequence was this, if I add that to a number, it's essentially like adding 0. What this means is, if I have an infinite geometric series that's decreasing each time like this, so these fractions are getting smaller and smaller and smaller and smaller and smaller, eventually the sum is going to approach something. Eventually the numbers I'm adding are so small that it's like adding 0, so I actually can find a sum for this infinite series, which is kind of crazy because it's infinite. But we can find a sum for it. And here's our formula. Our formula is my sum equals term 1 divided by 1 minus r. And now I want to tell you that this is only going to work if the r, or the ratio, is less than 1. I just put absolute values around it because I want the absolute value, or like the positive version of the ratio, to be less than 1. So basically it needs to be a fraction, like is r 1/2, is r 0.6, is r 0.1, something that's less than 1. And again, the reason I can actually find a sum, though it's infinite, which is totally crazy because it's infinite, but I'm still able to find the sum, is because eventually, if I get really, really far down into my sequence, the numbers that I'm adding each time are so small, it's kind of like adding 0 every time. And then let's look at another situation. Let's suppose that I went the other way around and I had this series. 2 plus 4 plus 8 plus 16 plus 32 plus 64 plus... The same rule does not apply because every single time here the numbers are getting bigger and bigger and bigger and bigger and bigger. And so actually we cannot find a sum if that is happening. So actually, if the absolute value of the ratio is greater than or equal to 1, we can't find a sum. Now, these rules you're going to want to have memorized. I will have this formula on the board, but I won't have these rules on the board, so that you're going to have to memorize. So here's the deal then. If I'm going to try to find the sum for one of these geometric series, every single time I need to determine if my ratio is less than 1 or if my ratio is greater than equal to 1. So let's go ahead and give it a try. And by the way, I can tell it's something's infinite, because remember, this new stuff I'm showing you right now is only for an infinite series. If it's a regular series, or if I'm only finding the first 25 terms of the series or something like that, then it's finite and use the rules we learned in 11.3. Alright, I can tell these are infinite right now because they have an infinity symbol on top of the summation notation. And then this is a typical geometric formula though, so it still is following these general rules. So right now term 1 is 3 and r is 0.6. So I'm going to ask myself again, can I find a sum or not? So the first thing I need to do is ask myself, is that a true statement? Yep. So it's less than 1, so I can find a sum. So let me go ahead and plug into my formula. Term 1 is 1. 1 minus r is 1 minus 0.6. And by the way, when I am dividing a number by a decimal, it's kind of like dividing it into fractional pieces, so it actually increases the number. So my sum this time is 7.5 for that infinite series. Alright, let's do another one. So again, I know it's infinite because it has an infinity sign on top. And now this is important because on the test it's not going to tell you what type of problem is what. So you need to be watchful here. So if it has the infinity sign, it's this type of problem, it's infinite. If it has a number there, then the same rules apply as section 11.3. Alright, anyways, A1 is 2 this time. R is 0.1. That is definitely less than 1. So I'm going to plug into my formula. Term 1 is 2. R is 0.1. 1 minus 0.1 is 0.9, and so I end up with 2.22 repeating. We'll round it to 2.22. Pause the video at any point if you need to, if I'm going too fast for you. Alright, let's move right along here. Look at example C. So again, it's infinite. Alright, A1 is 0.85. R is 2.4. Is that less than 1? No. 2.4 is greater than 1. So actually this has no sum, and that's your answer. And you might get an answer like that on a test or quiz. So an answer of no sum is appropriate. Alright, I want you to pause the video and try D on your own, and when you unpause, I'll have the answer revealed. Alright, there it is. S is 9. You are going to get the same type of problem, only represented in a different way sometimes. So let's look at E and F. Notice I this time know it's infinite because it has a dot dot dot, and the other reason I know that I'm going to think infinite is they did not specifically tell us to add together a certain number of terms. Because you can take an infinite series, and let's say I said add the first 10 terms or something like that. If I said that, you would use the formula from last time. Okay, but if they do not specifically say how many terms I'm adding or something like that, we can assume it's infinite, so I'm using my infinite rules that I just taught you today. This time, the A1 and R are not as obvious to find. Well, actually, A1 is as obvious to find, because A1's always the first term. But I will need to find R. So remember from last time, if I know two terms right in a row, I can just take a term and divide by the previous term. Okay, R is -1/4. Then in my mind I'm thinking, okay, is that less than 1? Yes, so I can find a sum, and I'm going to plug in then my A1 and my R. Careful with your double negative there. So I have 1 over 1 minus, and then in parentheses a -1/4. So I got a negative. Check that out. So 1 divided by 5/4 actually, and I end up with 4/5 for my sum. All right, why don't you pause the video and see if you can do F on your own, and when you unpause, I will have the answer revealed. All right, you should have gotten a sum of 18, and then if you're kind of thinking, wow, I don't really know yet exactly what you're doing, remember, we want to find what R is, and then if R is less than 1, I can find a sum. If R is greater than 1, I cannot find a sum. In this case, I could find a sum. So then I went through and I found what term 1 was, and then I plugged in term 1 and R into my formula. Pause if needed, but if you're ready, go ahead and flip to the back of this sheet of paper. I just want to show you one thing here with example H. Sometimes, I just want look at the difference between G and H. See how this one starts at 1 and the power is I minus 1. This one starts at 0 and the power is just n. And by the way, the variable is not important. Usually they use I, n, or k, but really they could use anything. Doesn't matter, so that doesn't affect our answer. But see the difference how this starts at 1 and then that's I minus 1. This starts at 0 and it's just n. These are actually the same type of problem. So this is still giving you information that A1 is 0.3, and it's still giving you information that R is 5. And it still works that A1 is 0.3 because if I plug in a 1, or you know what, I take it back. Instead, A1 would be the first term. In this situation, actually term 0 is the first term. And it is the first term because if I plug in a 0 here, 5 to the 0 power is 1. So 0.3 times 1 is just 0.3. And if I was going to find the sum for this, I would use that in my formula instead of term 1. I'd use term 0, kind of like what we were talking about yesterday a little bit. That is not going to come up too often. And then actually, I don't even have to find the sum because R is greater than 1 this time. So my answer for H actually is no sum anyways. All right, just to kind of use the formula in a different way, there's two other things that we're going to do today with this. First of all, we're going to be given a term and a sum and we're going to have to find R on our own. And then we're going to use this geometric series formula to write repeating decimals as a fraction. So two more things to do today. Go ahead and look at example 2. So now I am given term 1 and I'm given the sum and we're supposed to find R. So really right now they just want you to use this formula and work backwards and to try to solve for R. So it's just a way to use the formula in a different kind of format, just to practice using the formula, I guess. I know that the sum is 10, so I will plug that in for S. And it said that term 1 is 4, so I'll go ahead and plug in 4 there. And now I need to solve this. A note for you. Whenever I have a variable on bottom of the fraction, it's recommended that you make the other side be a fraction as well, and then I can cross multiply. 10 in fraction form would be 10 over 1. And now cross multiplying means I do 1 times 4, so 4, equal to the other cross, 10 times 1 minus R. And now actually this is a very easy formula to solve. So it's only the setup that's difficult. So 4 is equal to 10 times 1 is 10. 10 times negative R is negative 10R. Just don't be sloppy with your solving. You want to make sure that you get the correct answer. Don't make a silly mistake. I end up with 3/5 for my R. I'm going to do one more and then I'll let you try 2 on your own. So this time I know that the sum is negative 2. I know that the term 1 is, and you know what, this got cut off, so look at your page closely. It's supposed to be negative 4/3 right there. I should have changed that printing, but so it goes. So I got negative 2 equals to negative 4/3 over 1 minus R. I am going to cross multiply. Negative 2 times 1 minus R equals 2. 1 times negative 4/3 is negative 4/3. And you know what? Even though there's a fraction in there, we still solve it the same way I did before. So distribute the negative 2 and then solve. So add 2 to both sides. 2 is the same thing as 6/3. So I have 2/3 divide by 2 r is 1/3. I'm going to give you a chance to try this on your own now if you'd like to. So if you'd like to, pause the video and try C and D, and then when you unpause, I will have the answers showing. Alright, go ahead and check your answers for C and D. And make sure you write down any questions you might have that you want to ask me about tomorrow or the next time you see me. Alright, let's look at example 3. So now, here is a way that we could actually use this formula to help us out if I was on the MCA test or something. And this is to take a repeating decimal, and we're going to write that repeating decimal as a fraction using my sum formula. And now first it says though to write each as a geometric series. So there's actually going to be two parts to this question. So I want to just remind you that if I look at a decimal like this, the first number is in the tenths place, the second number is in the hundredths place, the third number is in the thousandths place, and so on. And so if I split these up, I could actually write this as 4 tenths, because it's a 4 in the tenths place, plus 4 100ths, because it's a 4 in the hundredths place, plus 4 1,000ths, because it's a 4 in the 1,000ths place, and so on. And that is my geometric series. So I just completed the first part of the question just right there. And now I want to write this series as a fraction. And in order to write this as a fraction, we are going to use our sum formula. And our sum formula, remember, I need term 1 and I need r. So obviously term 1 is 4 tenths now of this series I just created. But I need to find r, and remember, to find r, you could take any term. If I know 2 terms in a row, I don't have to use that fancy mn formula. I can just do a term divided by the previous term. So, and feel free to type this into your calculator if needed, but I've got 4 over 100 divided by 4 tenths. And when I type that up, I get 1/10 for my answer. So r is 1/10. Go ahead and calculate that out, and you end up with 4/9. So cool. The sum of all those is actually what it would be in fraction form. Kind of interesting. And then, real quick side note, there might be a problem or two that asks you to take this and write it in summation notation. So just a quick comment. First of all, this is going to be infinite, so I went from 1 to infinity. And then as soon as I know what term 1 and what r is, because it's geometric, I'm just using this normal formula here. So now the normal geometric formula, so now I'm going to just replace term 1 with what term 1 is. It's 4 tenths. And I'm going to replace r with what I found r to be, which is 1/10. So writing it in summation notation is actually not difficult at all. You just have to remember to write the sigma, and you have to remember that it's going up through infinity. And by the way, I just made a mistake I see here. Check this out. Remember, this right here is supposed to just represent what my variable is. If I use a variable of n, I should have n equals 1 on bottom there. There we go. Now it's correct. Alright, let me show you what to do when I've got more than one place value. So see, these are coming in pairs now, 3, 6, 3, 6, 3, 6. If I'm going to write this one as a series, I can think of it like, I can think of these together. So whatever the last digit ends at would be what fraction I would make it. What I mean is, this in words would be 36 100ths, because the last digit is in the hundredth place for just that little group of 3, 6. The second little group of 3, 6, the last digit is actually in the 10,000th place. So my second term would be 36 over 10,000. And every single time, I know there's not more 3 6s here, but every single time, see, I'm adding 2 zeros. So if I did need to write a third term, I would just take 10,000 and add 2 more zeros on it. So that would be 1, 2, 3, 4, 5, 6 zeros. So 1, 2, 3, 4, 5, 6. Okay. So actually it'd be 36 1/millionths. So that's my series. Term 1 is 36 100ths. And then again, I need to find r, and this time, the bottom number is increasing by 100, and if you just do term 2 divided by term 1, you would also get 1/100th. And I want you to do that in, let's do it in fraction form so it matches. So I've got 36/100ths over 99/100ths. Anyways, that is going to reduce to 4/11ths. And if you needed to do it in sigma notation, once again, I go from 1 to infinity, and then I put term 1 here, and I put r here, and that is not r. r is 1 over 100. There you go. Pause if needed to write that down, figure it out, rewatch it, that little clip, whatever you need, and then go ahead and flip to the back page. Keep listening, because these are going to be more challenging on the back here. What's happening on the back is my repeating decimal part doesn't start until right here. So here's what that means. Excuse me. I'm actually going to have 2 fractions that I have to add on after, and I can actually only find the sum of the part that has the repeating decimal. So let me show you what I mean. I got a 4 in the 10ths place, so that's going to be 4/10ths. I've got a 1 in the 100ths place, and then I have a 6 in the 1000ths place, a 6 in the 10,000ths place, and so on. But right here is only where it's going to be the pattern. So I'm actually going to right now ignore these first 2, and I'm just going to use my sum formula on this stuff. So if I'm only looking at this part of it, term 1 is 6/1000ths, and to find r, I can do a term divided by the previous term, but now let me show you a shortcut since we've done this twice. The bottom number is just increasing by 1 0. That would be increasing by 1/10th. Or I guess decreasing by 1/10th, depending on how you want to think about it. So here's the deal then. Just the sum of this part is going to be 6/1000ths on top, and then 1 minus 1/10th on bottom. And that is 1 over 150 if I type that all up into my calculator. So I just found the sum for just the repeating sixes part. Now I go back and use the stuff from before. So that is just still there because that was part of my fraction. And so I add all 3 of those together to get my final answer. All right, so one more problem. This one is similar to C, but I have this number in front, and that's a whole number, so that's just the number 3. So that is the part that we're going to ignore at first this time, and we'll add that on at the end. And then my repeating pattern starts happening right here. And now look at this. There's 3 digits for each one of these like segments, and again, the bottom number of your fraction is where the last digit is. So this 2, it's in the thousandths place. So I'll say 882 thousandths. And then 1, 2, 3, 4, 5, 6. The 6th decimal place is the millionths place. So I've got 882 1/millionth as well. So that is my series. And now, kind of like we did for example C, I'm just going to find the sum of this repeating part. And term 1 would be the first part of this repeating part I'm trying to use. And then look at this. On bottom, it's increasing by 3 zeros. So R is 1 over 1,000th. 3 zeros. So 1 minus 1 1,000th. Anyways, okay, I end up with, let me calculate that out here. All right, I got 882 1,000ths divided by 1 minus 1 1,000th, and I end up with that, I'll convert it back to a fraction for now, so that is 98 over 111, but notice I need to use this guy. So 3 plus that to get my final answer. And, you know, I don't know. There's a few different correct ways I would accept this. If you left it as 3 and 98 111th, a mixed fraction, that would be okay too. But in regular fraction form, that is the sum. And oh, actually, and our whole point was to write it as a fraction. So I do want to write it as a fraction. All right, write down questions you have. Thanks for listening. Example 4 we will do in class. See you again soon.